Okay, now oxidation numbers. Basically turn that fairly fluffy idea of losing and gaining electrons into something a little bit more concrete, which will give us the tools to write equations. So oxidation numbers allow us to look at an equation and classify that reaction as a redox reaction and work out what's going on, even though we don't have ions with charges as we did in those previous examples. So it involves following a series of rules. Now, we'll go through the rules. They're not actually that complicated once you go to try them out. Once you get a bit of practice at them, they're pretty simple. But we'll just run through them first and then we'll do some examples. So, first of all, free elements, oxidation number of 0. By free elements, we mean pure substances, pure elements from the periodic table. So all the gases, oxygen, hydrogen, nitrogen, etc. All the pure metals, magnesium, copper, sodium, silver, whatever. In the metallic form, where they're neutral, they've got oxidation numbers of 0. If it's an ionic compound, then the oxidation number equals the charge on the ion. So, because you all know your valencies, that'll be easy to work out. Aluminium oxide's made up of Al3 plus ions with an oxidation number of +3, oxide ions -2, magnesium bromide 2 plus and 1 minus, etc. Then we get where we've got compounds involving non-metals. Well, two really common elements are hydrogen and oxygen. Now, hydrogen almost always takes +1 when it's in a compound. Oxygen almost always takes -2 when it's in a compound. Now, of course, if it's a pure element like hydrogen gas or oxygen gas, it's going to be 0. But where we've got it in the compound, hydrogen is almost always +1, oxygen is almost always -2. Now, there are compounds for both in which it's different. Metal hydrides, we've got the hydride ion, H-, that's one exception. And for oxygen, it's in peroxide compounds, in which oxygen is -1. And they'll always be given to you with the word peroxide in the name, and year 11 in particular, you won't be asked to worry too much about those. So for all intents and purposes, hydrogen is +1, oxygen is -2. Simplest example of that is water, in which hydrogen is +1, oxygen is -2. Now that will often leave you with one element you need to find out the oxidation number of. So you do a little bit of a sum, you do a little bit of arithmetic, and it's based on the fact that if you've got a neutral compound, the oxidation numbers will add up to 0. If the overall thing you're dealing with is an ion, then the oxidation numbers will add up to the charge on that ion. And again, that'll become more obvious when we see a few examples. Now, the last little tricky bit is when you get combinations of two of the really strongly electronegative second period elements. Chlorine, fluorine, oxygen. Well, the strongly electronegative elements anyway. When you've got a combination of two of those, the one that's the most electronegative of them takes a negative oxidation number as if it was an ion, and the other one works out to balance the oxidation numbers. Now, remember that fluorine is the most electronegative element, followed by oxygen, followed by chlorine. So if you've got a combination of fluorine and chlorine, fluorine's going to be negative, chlorine's probably going to be positive. Same as if you've got oxygen and chlorine. Oxygen will be negative, chlorine will probably be positive, and so on. Okay, examples. Potassium phosphate. So what do we know about potassium phosphate? Well, it's a neutral compound, no charge there, so the oxidation numbers are going to add up to 0. We know this is an ion compound made up of potassium ions and phosphate ions, so we know what potassium ions are, they're K+, so the oxidation number will be +1, because it's a simple ion, we know the charge and we know the oxidation number. Oxygen in a compound is -2, always, almost. That just leaves us with one element to work out, the phosphorus. So given those two, given the fact we know they're going to add up to 0, we can work out what phosphorus is. So you set yourself up a little sum. So we've got 3 potassiums, 3 times +1 gives +3. The one phosphorus we've got, we don't know what that is, that's the unknown, the X. We've got 4 oxygens, 4 times -2 gives us -8. Now we know because it's a neutral compound, those 3 terms will add up to equal 0. What is the phosphorus going to be to satisfy that? Clearly +5. So then we write the oxidation numbers when we're writing the oxidation numbers with a compound. Write up the oxidation number of each individual potassium ion, each individual phosphorus, each individual oxygen. Okay, this time, what have we got? We've got a compound with an overall charge on it. So we know that the oxidation numbers for this one will add up to the charge on the ion, -2. Oxygen is going to be -2, each of the 3 oxygens is going to be -2. So we'll do the arithmetic to work out what the sulphurs are. And this time we've got 2 sulphurs, we don't know what they are. The 3 oxygens give us -6, adds up to -2. That means the 2 sulphurs have to be +4. Each individual sulphur is going to be +2. So that's how we write it. Okay, now our example of a combination of strongly electronegative elements. Now, it's a neutral compound, oxidation numbers will add up to 0. Now, fluorine and oxygen. Fluorine's more electronegative, so it's going to be like the fluoride ion, it's going to take -1. The sum, therefore, will give us oxygen equaling +2. Okay, just a couple of things to note. Oxidation numbers are just numbers, so we write them as numbers. They're theoretical constructs, they have no real meaning. So we write them as numbers. +4, -2. Positive and negative numbers. Charges on ions are real physical things. They're properties, electrical properties of chemicals. So we write them as numbers of positives, numbers of negatives. The ion 3 ion has got a charge of 3+. That's a physical property, so we write it as such. Now, as you've been seeing, I've been writing the oxidation numbers above the compound, because when you're working with equations, that's what you do to see what happens. So each individual nitrogen is +4 in this case, each individual oxygen is -2. Don't be lazy and do your arithmetic up there, because you'll end up not being able to follow across the equation what's going on. Do the arithmetic somewhere else. What you write up above the compound is the oxidation number of each individual atom. And then onto the questions.